I'm Yann Gouttenoire. I'm a postdoc in Tel Aviv, and I'm interested in DSM, early universe physics, but also lately late universe physics.
And you're going to tell us today about...
And today I will tell you about primordial black hole formation during supercooled phase transition. And thank you, the organizers, for making this workshop happen. It's wonderful. So it's a work done with Professor Tomer Walensky. So first, let me remind you what is a supercooled phase transition. So basically, it's a phase transition of first order, which is hierarchical, which means you have two scales with a large hierarchy between them. So the first scale is Tc, the critical temperature, when the two minima of that potential driving the phase transition coincide, right? So at high temperature, I have to direct the pointer there, right? I have to be close enough. I see.
But it's working before, no?
You can go backwards, but you can go. That's it. So
No,
I can go both, but there is some delay. If you, I have to act before I talk.
You can also go and press.
Yeah.
But,
It's there is no.
It's a bit more annoying. Every day.
But the same, it doesn't go.
It should not.
There is going to be a shortcut. Okay, it's just delay. Let me try. I have to push with more strength. Okay. Oh,
here we go.
Okay, I will describe the slide like this. So top to bottom is evolution as the temperature cools down. At high temperature, the universe is stuck in the first vacuum, right? And then as we cross Tc, when the two minima coincide, below Tc, the first vacuum becomes metastable, right? And a supercooled phase transition is when the second scale of the problem, which is the nucleation temperature, is much smaller than Tc. And in between those two stages, the universe is dominated by the vacuum energy of the phase transition, the delta V here. And at T-nuc, when the nucleation takes place, the vacuum energy of the phase transition is released into heat to reach the universe. And how does it happen? It happens by bubble nucleation, which then expands and collides and percolates the whole universe. So you see that a hierarchy between the two scales implies a period of vacuum domination, because the temperature when the universe becomes vacuum dominated coincides roughly with Tc. So below Tc, you are vacuum dominated, you inflate till you finally nucleate. So that's a supercooled phase transition. What kind of particle physics model can lead to this? So there are two classes of models of phase transition in the literature. First are polynomial potential, right? Pi squared, pi cubed, pi to the 4. And on the left is the potential plotted for different temperatures. You see, I decrease the temperature. Initially, you are stuck in the first vacuum, but when the temperature is smaller than critical temperature, this first vacuum becomes metastable, and you want to nucleate. When do you nucleate? This depends on the bound section shown on the right. Bound section is the amount of action cost for nucleating a bubble, and you want it to be as small as possible. And you see, as you decrease the temperature, the cost for nucleating decreases. And at some point, it can compete with Hubble expansion around this horizontal dashed line, and then you can read the nucleation temperature. Let's read. Okay. And this is the trajectory in field space of nucleation. Okay, that was the story for polynomial potential. Now we'll compare with the second class of potential, which are nearly conformal. So here you see that the quadratic term is equal to 0, and instead, spontaneous symmetry breaking is induced by radiative correction here by the running of the quartic. So you have a logarithm, okay, which is non-polynomial. So let's compare. So the first comment is that the bounce action decreases very slowly with temperature. For polynomial potential, the bounce action was decreasing as a polynomial with temperature, and now with this nearly conformal potential, the bounce action decreases logarithmically with the temperature. So then you need to cool down a lot to be able to reach the critical temperature and nucleate. So you can compare the nucleation temperature for the orange case, polynomial, right? You have no hierarchy between TC and TNUC. While for nearly conformal potential, because of the log, you can generate a large hierarchy between TC and TNUC. Supercooled phase transition are described by large alpha, so a large latent heat release. This is the delta V, the vacuum energy difference of the phase transition, normalized over the radiation energy density, super large, because it is set by the ratio of scales, again, which is large. And there is a small beta average. Beta is if you want, the time derivative of the bounce action. But the bounce action, we said, decreases very slowly with temperature. So when you take its time derivative, you get a small number. So beta average is small. So large alpha, small beta. So this is the take-home message. Supercooled phase transition arises in presence of flat direction, zero quadratic term, right? A flat direction broken by logarithmic term, and they are strong, large alpha, and slow, small beta. What kind of particle physics can generate supercooled phase transition? So at dimension d equal 4, and if the radiative correction are weakly coupled, you have the one loop Coleman-Weinberg expression here that you must recognize. And in the strongly coupled region, instead, you can also have a nearly conformal invariance. For instance, if your confining sector confines, so its coupling constant becomes large while its beta function is running close to zero, then you have an approximate scale invariance that gets spontaneously broken by your confining dynamic. Then you have PNGB, pseudo non-Gouttenoire, which is a light dilatant that can efficiently describe the dynamic of the phase transition. And those two cases are related in the limit of small anomalous dimension, epsilon goes to zero, Coleman-Weinberg light dilatant, they match. And then a third scenario giving rise to supercooled phase transition that we can see in the literature are the one occurring at d equal 5, when you take two d equal 4 slices in a warp the fifth dimension. And those two scenarios can be related by holography. Now let's discuss what are the cosmological consequences of supercooling. One is missing. Large gravity wave spectrum, direction of colleagues, relativistic bubble walls, high energy particle productions, and finally, which is the purpose of my talk, primordial black hole production. So there is a large gravity wave spectrum. Why? This is the formula for gravity wave from first order phase transition. So first, you have a normalization factor with respect to the current radiation density, 10 to the minus 5. Then we have this alpha factor, which stands for how much scalar field is contained in your universe at the time of phase transition. So for supercooled phase transition, it dominates the whole budget. So this factor is 1. Then you have the bubble size. And for supercooled phase transition, the bubbles are maximally large. And then you have a bubble velocity, and for supercooled phase transition, velocity is maximally large because they evolve in a dilated plasma. So there is nothing to stop those bubbles. And then when you plug the number, you get 10 to the minus 8, which is very, very large. Sorry? Oh, yes. Thanks. Okay.
Much better?
I think it's the computer.
With the computer? Probably the talk. The slide. Okay.
So
Okay, thanks. So you see that the signal for supercooled first order phase function is maximally large. So would be detected by any experiment and is above all foreground, all astrophysical foreground. So will be ruled out very efficiently in the future. Or discovered, but we never know. Second consequence of supercooled phase function is a dilation of colleague. Why? Because so during a phase function, there are two components in the energy density. There is a vacuum component shown in dotted, and the radiation, the heat, which is shown in solid. And you see that you have a period of vacuum domination, dotted is above solid. So radiation is rejected away, inflated away. And then when nucleation and percolation takes place, the vacuum energy is converted into heat, and you reheat the universe. And this reheating injects entropy in the universe. That you can introduce this ratio of entropy, D, which is given by the ratio of temperature to the cube. And because you have a large hierarchy for supercooled phase condition here, you have a large entropy injection. And you can use it to dilute any relic, for instance, dark matter, and you can evade the unitarity bound on thermal dark matter, Grace and Kaminkowski, 91. They use unitarity to constrain the mass of thermal dark matter, which should be smaller than 100 TeV. But if you reheat this dark matter after it is produced using this kind of dynamics, then you can have larger dark matter mass. There has been a series of work on this. Now I move to the third consequence, relativistic bubble wall. So during a phase transition, so you have bubble wall nucleation. And what is bubble wall? It's just a domain wall separating two domains, and those two domains, they don't have the same vacuum energy. So you have a jump in vacuum energy, and this generates a pressure, an expanding pressure. The bubble wants to expand with a pressure which goes to Tc to the 4th, but you have to compare this. Oops. You have to compare this driving accelerating pressure to possible friction pressure coming from interaction of bubble wall with the plasma. And in 2009, Bodecker and Moore derived this expression due to single particles acquiring a mass delta m inside the bubble wall. But you see that if you have a large hierarchy between T nu and Tc, as it is for supercooled phase condition, then the friction in red is much smaller than the driving pressure in blue. The bubble should expand forever. But then in 2017, the same authors, they introduce next to leading order term in gas coupling due to particles, when they enter the wall, you see, they can radiate Bremsstrahlung. And this Bremsstrahlung can acquire mass. And this is enhanced, this is suppressed by G coupling, but enhanced by gamma, the Lorentz factor of the bubble wall. So as the bubble wall goes, as the Lorentz factor goes, at some point this term should compensate the blue. And this computation was done at the perturbative level, but we have checked that it stands when we do Sudakov estimation. So an arbitrarily large amount of radiation, can radiate 1, 2, up to n quanta, and then you reason n to infinity. And we also checked what happened if there's such a large coupling between the particle and the wall that you can flux tube attached to the wall, as it should be the case for QCD-like first order phase condition. And the same results stand. You just replace G by 1. So this is the result. You see that you can reach very large gamma factor, 10 to the 10. So you have macroscopic objects propagating in the whole universe with a gamma factor, a Lorentz factor of 10 to the 10. So these are very violent events. And in the next slide, I show you some application of this. But there are still, so this was a very interesting computation to do, but there are still open problems. For instance, this expression that was gotten in 2017, the one we got last year, is not gauge invariant. So nobody managed to get something gauge invariant yet. There's been some attempts, but it doesn't work because we think that to get something gauge invariant, you should contact the wall because some gauge degrees of freedom are hidden inside the wall. So if you treat the wall as the background, no way you will get something gauge invariant at the end. So this is something which should be done.
Sorry, out of curiosity, that when the attempt, do they view it as an attempt, or do they view it as being successful?
I think it took some time for them to accept, but I think I'm not sure yet. But I think I discussed with Jessica. I think she thinks they think like us. They think we agree. Yes, I think it's very clever what they did. Very clever. Much more clever than what we did. We use very simple formalisms, and they use very sophisticated ones. But at the end, the result is not consistent. As a comment by some other papers, some other paper made some comment that the results were not consistent. So what we did is just apply some Peskin and Schroeder formalism of Stoichkov summation, and we found something which agreed with Bodecker and Moore, and a result which sounds critical, but which is not gauge invariant. In that case, they obtain something which is gauge invariant, but which is not critical in the limit where the value is set to 0, because if you make the bubble wall invisible, so you set the value to 0, the pressure remains. The pressure term remains. So that's why it cannot be consistent. So, but we don't know yet how to quantize the wall to incorporate the gauge degrees of freedom. So what are the implications of those fast, very relativistic bubble walls? So high energy particle production. Why? Because of this Bremsstrahlung radiation, particles enter the wall. They radiate Bremsstrahlung, right? But what we found is that the emission is preferentially soft, which means that it is produced at rest, not at rest, in the bubble wall frame, this radiation. Then if you boost it to the plasma frame, this radiation should follow the wall. And also, like, some of it is so soft that it cannot even penetrate inside the wall. It gets reflected because this radiation acquires a mass inside. Let's assume it. If it acquires a mass, it needs to have kinetic energy large enough to afford it. If it doesn't afford it, then it gets reflected. So then you have a whole set of quanta that follow the wall. Okay, first channel of production. The second one. The second one is now if you have a confining type phase transition, then the quark will interact very strongly with the wall. And then they will form a flux tube attached to the wall. This is one single quark entering inside the wall. It forms a flux tube attached to the wall. This flux tube fragments. And then you have all of those fragments that will follow the wall, because those fragments, they are produced in the string rest prime. And the string rest prime follows the wall. Plus, you have one quark ejected, if you think about it, because you have to conserve color. So you have one color entering. Fragments are color singlets. This is one color singlet, a second color singlet, you see. Red and green is one color singlet. Green and red, one color singlet. So this green has to go out. So those are all types of particle production at the wall interface. And I know that Maximilian and the student of Filippo is working hard on this. But there are other ways to produce particles. You don't need a plasma to produce particles. those are interaction with the plasma. But what if there is no plasma? Just bubble wall in vacuum. There should be also be particle production because the wall can decay. Because the scalar field, there is no reason that the scalar field is stable. And if the scalar field can decay, then what happens? So here we are solving the Klein-Gordon equation for a thick wall. Thick wall, it means it's if you look at the wall profile, you will see in gray, this is the field value is many oscillations. And this is how the wall profile looks like in field value in gray. And in terms of energy density, look at blue. So this is the wall profile in terms of energy density. But now what happens if you introduce the wall decay? So now we allow the phi to decay, and then you see that part of the energy density of the wall, so blue becomes pink. So if you do the difference, blue minus pink, you get missing energy, which goes into decay product. So the wall decays, and this decay product should follow the wall. And let's see. Yes.
What's the time scale here?
So it's S, it's light cone coordinates, square root t square minus r square, and Tn is T mu, the nucleation temperature. So the wall profile, you see, is 10%. The wall thickness is 10% of the nucleation temperature. Inverse. But there are other possible. What if you do not decay at all? So here is some idea. So the bubble wall expands, right? Is accelerated. So if you go to the bubble wall frame, you have an accelerated observer. So you should see Unruh radiation, and this Unruh radiation, part of it will interact with the wall. It's some type of boundary condition for those quanta. And then you could expect this Unruh radiation to have an impact on the wall motion, but also those quanta to be observed, possibly in the plasma. And another source is dynamical Casimir, because inside the bubble wall you have some modes. The cavity has some mode, right? But as the bubble wall expands, the mode varies. They possibly vary non-adiabatically. So then this should what was considered as a vacuum at some stage of evolution. At a later stage, when the bubble has expanded by a lot, if you want to map the state of the quantum field inside the bubble wall at small radius and the quantum state of the field at large radius, you should do a Boggle-Bott transformation because of the non-adiabacity of the evolution, and this should fill your mode with quantas. These are similar to dynamical Casimir in condensed matter. But I expect those are highly non-trivial and needs more work.
What's the rationale to think that they would be relevant?
So there are different ideas here. So first is to have a new channel of particle production of particle following the wall, which will be useful for what I will show in the next slide, which is scattering of those shell of particles together to make a particle colliders, cosmological colliders, because as the wall collide, each particle created by the walls will also collide, and you will have a particle, a cosmological collider of high energy. This is the next slide. Another application is, what if you have only one bubble that nucleates? So generally we say, oh, only one bubble, the phase transition do not complete, so this universe cannot contain observer. You get stuck in the first vacuum. Yeah, but what if in this single bubble you have particle production that is able to reheat that single bubble? What if that single bubble is actually reheated? Then it means could be filled with something. Observers. Maybe not our universe, because we don't expect the radiated plasma to be homogeneous, because as the wall expands, a new particle are generated, but in the meantime, particles formed at the center start already to cool, so you will have a whole gradient of temperature. So unfortunately, this might not be efficient to explain our universe. That might still have an implication for the landscape, for instance. Like which part of the landscape generates observers and which do not. Now I move to the next slide. So this is a picture of the tevatron. So it's two synchrotrons, 1 and 2. Each one accelerates its particle, and then the particle collide. So now there is a bubbletron, which is a two bubbles. Each one accelerates its own particles, and then as the bubble collide, they will scatter their shell of particles. And if you compute the energy in the center of mass frame of those shell particles, if you plug gamma equal 10 to the 10, right, Tc 10 to the 6, you get 10 to the 16, so you can reach the God scale with this bubbletron. And I expect this to be kind of independent of the channel of production that I've shown earlier. Maybe it does, but I expect this formula to. I just don't know about the vacuum, the Unruh radiation and dynamical casimir. I don't know if this formula holds, but for the other one, it holds. That's the same formula. So now I move to my talk after this short introduction. So how to produce primordial black hole with a bubble. So this idea is not from us, unfortunately. I have to give credit for that group. I think it's a very clever idea. I'm very fan of it. So the idea is to use a fluctuation of the percolation time to produce PVH. So today we're in Madrid, right? Let's do a small thought experiment. We look at our past light cone. So we look at the sky. And in particular, we look at the space-like surface when the universe was electronic old. Okay? And now we do, okay. And this space-like surface contains 10 to the 40 causal patches. You might know that CMB sphere, on the CMB sphere, there are 10 to the 4 imprinted causal patch, but if you go deeper in the past, you have goes like T cube. This number of causal patches goes like T cube. So if you reach at 8-foot scale, this space-like contains 10 to the 40 Hubble patches. It's a lot of Hubble patches to see. So you look at each of them, and now you assume that at the electronic phase transition, at the electronic scale, there was a phase transition. Okay? So all those Hubble patches are stuck in the false vacuum, but they are ready to tunnel. They are ready to get percolated by the new phase in yellow. Okay? So this is what you could expect. Blue becomes yellow for all those 10 to the 40 Hubble patches. But actually, when you think about it, the time for bubble to percolate, it's a stochastic variable. It's not fixed. It's not one value. It's a distribution of values. Why? Because each individual nucleation of bubbles is stochastic. You have to play dice. Every time you nucleate, you have to play dice. Okay, I choose one bubble. When does this bubble nucleate? I play dice, you get one number. Okay. You get one number along this curve. Every time you nucleate a bubble, you get one nucleation time distributed along that curve. Then those bubbles, those 1,000 bubbles, get nucleated along that curve. Then they expand and percolate, but then the resulting percolation time will be stochastic, will follow from the curve. So then what does it mean? it means that those 10 to the 40 Hubble patches, they do not percolate at the same time. While most of them are already percolated, most of them are yellow, some of them, some late birds, they are still in blue. They are still in blue, so they are still in the old phase, so they are still expanding. They are still inflating. While the yellow, they're already cool, like radiation. And then it means that finally, when those late birds percolates and convert their vacuum into radiation, they will induce hotspots over density of radiation because they have percolated later, they have inflated during a longer time, and while they were inflating, so keeping their energy constant, all the neighbors were cooling while their energy was constant. So they are hotspots. Actually, it's not that they are hot, it's like everybody is cold because they were keeping their energy constant while everybody cooling. So they are, yeah. But then, so you have hotspots. And if the hotspots, if the contrast density is above 40%, you form black hole. Yes, that's the story. And okay, let's look more quantitatively now. So this, as I told you, are the two components of the energy density of the phase transition. Dotted is a vacuum energy, solid is a radiation energy, and these two lines are critical temperature when you start inflating, and this line here, or this one, is when nucleation starts to take place. Nucleation starts to take place, so bubbles, they start to fill the whole universe, and percolation takes place here. And you see that during this this rise, the vacuum energy is converted into heat, and you heat the universe. So this blue curve is average over the 10 to the 40 Hubble patch. Now I will pick some of the late bird. Okay, let's plot the same curve for the late bird. In red is a late bird, so you see it starts nucleating later. So why all the neighbors are already converting their vacuum energy, this one, this late bird, is still inflating, and then starts to read later, and then this generates a contrast density. When you do the ratio of the two curves, I do the ratio late bird in red over the neighbors, the cooled neighbors in blue, I get green. And if green is above 45% or 40%, you form a black hole. And here I have chosen the delay of nucleation to be exactly such that we live at the boundary of black hole formation. Because the ratio of the two curves is exactly 40%, which is at the edge of black hole formation. And now, if you want to know what is the abundance of those black holes, you need to know what is the probability that this delay takes place. So you play dice, you find no nucleation, you play dice, no nucleation. Finally, your first dice gives you nucleation. What is the probability that this can happen? It's given by this curve, which is the distribution of nucleation time. And in dice black here, vertical, is the nucleation delay which is needed to form the first black hole. So you see, you read the probability here, you read 10 to the minus 10 or beta over h equal 8, but as soon as beta over h is 10, you see, you just go from 8 to 10, you see how the probability drops very fast, from 10 to the minus 10 to 10 to the minus 23. So it's very sensitive. The probability to form black hole is very sensitive in beta over h. I pass the details and I'm almost done. This is beta over h. So this is a plane, beta over h versus alpha, the two well-known parameters of phase transition. Every model can be mapped on those two parameters, and this is the constraint on PBH overproduction because you overcload the universe. So you see that bit average cannot be smaller than 8 or 9. We can trade alpha for TU over TC. I find it easier to understand. It's a ratio nucleation temperature over critical temperature. In other words, the amount of supercooling from right to left, and you see that bit average cannot be smaller than 9. It's nearly flat with the amount of supercooling because it mostly depends on bit average. Then, what are the masses of PBH that you can form? So here are the well-known constraints on PBH. You see that a supercooled phase at QCD can explain LIGO. One at the electroweak phase function can explain microlensing event. And if you want to explain dark matter, you have to go above 10 to the 5 GeV for the phase function scale, TC. And this is what we propose, because microlensing experiments, they have claimed, believe it or not, that they have detected PBH. They claim to have detected 3 candidates of PBH between 10 to the minus 6 and 10 to the minus 8 solar masses. Ogle HCC and HCC, so these are two events. I mean, I think there are 2 events around 10 to the minus 6 and 1 around 10 to the minus 8. So this roughly corresponds to the mass of the Earth and the mass of the Moon. For a black hole horizon of 1 centimeter and 0.1 millimeter. Okay? But you see that if you want to explain those events with early universe physics, you need something to take place at the TeV scale, between 100 GeV and TeV. So this corresponds to the mass inside the horizon at 100 GeV, and this is a mass inside the horizon at TeV. Mass of the Moon, mass of the Earth.
So you couldn't explain both with a single distribution?
No, you have to decide. You have to pick one. Or you have to just do supercooled phase function, but it's a bit too much. 2 steps, maybe, I don't know. So then you take a stupid model of supercooled phase transition, right? Where the electroweak sector is nearly conformal, so you introduce the second scalar, which transforms under some SU2 dark, and you set all the quadratic terms to 0. You assume that this model lives along a flat direction, and this flat direction is broken by radiative correction, because you assume the gauge coupling in the SU2 dark to be strong, so large alpha D, so large beta, so large loop correction. Okay. And this is a prediction of the model. You see that you can get beta average around 10, no problem, with that model. And here we one comment. So this is different TCs. And one comment is, you see, you have dotted and solid. Because in solid, we introduce catalyzed by QCD. Because if it is really electroweak standard model, then you cannot neglect catalyzed by QCD. So this limits the value of beta H that you can get. You cannot get arbitrarily small beta average if you catalyze by QCD, because it means that you cannot have arbitrarily large QCD. So you cannot have arbitrarily large supercooling, because as soon as the nucleation temperature reaches 100 MeV, which is around there, QCD can trigger the electroweak phase transition. But still, with this taken into account, you can still explain the events, microlensing. And you can have a prediction for dark gas coupling. And that's all. And I just say that if you want to know more about supercooled phase transition, I recommend this book. We discuss this standard model elementary particles, cosmology. It's a review of the different topics, thermal dark matter, first order phase transition, and cosmic strings. And this section 6.4 is about supercooled phase transition. And I conclude. So this, I discussed 5 consequences of supercooled phase transition. First, large gravity wave due to this large alpha and small beta. Then dilation of helix due to entropy injection following reheating. Then bubble walls are highly relativistic because the plasma is diluted, so cannot stop the wall. So you can reach Lorentz factor 10 to the 10. Macroscopic domain wall moving very fast in the early universe. But then they produce high energy particle production, easier due to interaction of bubble wall with the plasma, or interaction of bubble wall with the vacuum by its decay or by non-adiabatic processes. And finally, you can produce primordial black hole production. So you can produce primordial black hole. Why? Because the expansion of the universe of those 10 to the 40 Hubble patches that I've introduced is controlled by dices, by throwing dices, controlled by a low number of randomly nucleated bubbles. So for supercooled phase transition, I didn't say, but it's very important. The number of bubbles is very low. It's very low. It's given by beta over h cubed. For supercooled phase transition, beta over h is 10. So you have roughly 1,000 bubbles that nucleate in the Hubble patch. So you have to throw the dices 1,000 times, but this is a small number compared to typical phase transition where beta over h is 10 to the cube, let's say. So then you have 1 billion Hubble patches. Then the stochasticity of those 1 billion bubbles is lost because you know like the width will go like square root of 1 over square root of n. So for large n, you lose the stochasticity. Why? For supercooled phase transition, you have only 1,000 bubbles nucleating. So you still have some stochasticity, and the percolation time is not well defined, and you can have contrast density of the radiated surface. Thank you.
Are there any more questions for him?
Very basic, but what's the difference between nucleation and percolation?
Thanks. Nucleation is when you nucleate a bubble, like that's really the instanton going from nothing to have a bubble at rest, very small, microscopic. And percolation is a second stage where after that those microscopic bubbles have expanded till macroscopic or cosmological distances and have met each other. And when they met each other, then they eat up, they end up eating up the whole Hubble patches. And when there is no false vacuum region remaining, when everything is contained inside the individual bubbles, then you call it percolation. Please.
The black holes that form this way that we talk about, are they likely to be spinning or not spinning?
Good question. I expect that they don't, but I'm not sure because it's like the whole Hubble patch is falling. And what is the angular momentum of one Hubble patch? I would say it's 0, but I don't know. Never thought about it. Because the bubble, okay, the 1,000 bubbles percolating with each other, can it induce angular momentum? I would expect no, because they start from their individual rest position after nucleation. They start at rest, so there is no angular momentum. So where does the angular momentum can come from?
I don't see. I don't know. Maybe you have an idea. I don't know.
Well, just I think there are probably two opposite guesses. Now, one is to rely on a very rare large fluctuation. But then those tend to be spherical. On the other hand, they do form in a very messy environment with all these bubbles and turbulence going on. So it's conceivable in the end to gain some effect.
I see.
I don't know.
I see. Okay. Thanks.
Okay. So I think we can thank Yann again.
Thank you.